So I'd like to thank the organizers for this, what looks to be a wonderful week of discussions and talks on these spin-orbit coupled Mott insulators. And what I'll discuss today kind of builds on the two talks that we heard this morning from Ginyat and Liviu. And I'll kind of discuss hidden orders in systems, referring to multipolar physics, and sort of how one could potentially kind of look at strain and phonons as a way of probing or even sort of controlling the physics of these multipolars. Right, so the research in my group, just to introduce myself, is kind of, this is what I'll talk about today, sort of multipolar magnets and connection to what people have been calling alter magnets. But other things that we've been working on in the group has been looking at sort of non-equilibrium dynamics of spin-phonon coupled systems and multipolar phonon coupled systems. And a little bit I'll touch upon this towards the end. But some of this work got started thinking about things like pump probe experiments on these 2D van der Waals systems that Ginyat mentioned towards the end of his talk. The other thing we've been looking at is kind of topological magnetic textures and asking how electron-electron interactions can kind of modify the physics of Chern bands in these systems. And finally, quantum spin liquids, looking at some of these variants of these ilmenite compounds that Ginyat mentioned about, thinking about these cobaltates and how they might be potentially interesting spin-orbit-driven physics in these systems. So I thought I should Google hidden order, and this is what pops up. The first thing that pops up is, of course, it's a thriller, some very popular book, apparently. And maybe one should think of, looking for hidden order even in physics as kind of a way of an interesting, some kind of detective work that one has to do. The second thing that pops up is, probably relates to funding that we have to get to look for hidden orders in experiments. But here is kind of the more serious take on this, which is that there are these multipolar orders that we heard about, and they feature a strong entanglement of spin, charge, and orbital degrees of freedom. And although these were first proposed in these actinides or these F-electron systems where one sees a signature of a phase transition in thermodynamics, but it's very hard often to unravel the precise nature of the order parameter involved. And this is because this spin-orbit coupling entangles many of the degrees of freedom, and we have to find new ways to detect it. And potentially, it's useful to expand the class of materials where such multipolar orders could be found. And maybe one can think of these multipolar orders potentially as kind of new degrees of freedom. And if you have new degrees of freedom, you might think, well, maybe there is a way to kind of store information in these new degrees of freedom. And maybe if one can find ways to manipulate this, then it's a useful thing as well. So let's kind of look at sort of other than spin-orbit coupled systems. There's in fact closely related examples of what are called these spin alter magnets, which you might think of as just ordinary ferromagnets, except the ferromagnetic order is hidden in them. So here is like a toy example where you can have local sort of antiferromagnetic order on these little clusters. But if you look at the magnetic order here, it's translationally invariant. So it's a ferro order in that sense. But nevertheless, it breaks certain crystalline point group symmetries where if you do a C4 rotation about the center here, the red and blue refer to spin up and spin down electrons. Then you have to do a C4 followed by time reversal symmetry in order to get back the same pattern in the system, right? So an alter magnet, you can either view it as a D-wave ferromagnet, so it kind of changes sign under 90-degree rotations about the center of this plaquette, or equivalently, you can think of it, and I'll make this connection more clear in terms of octopolar order. And in fact, there's a lot of interest in this from some early work from Steve Kevelson and collaborators, but more recently in the context of spintronics, it's kind of been revived partly that you can have interesting momentum-dependent spin splitting of the band structure. these things also have interesting physics, which I'll point out analogs in these multipolar orders, which is that if you take certain surface terminations of these systems, you can have net magnetization, even though the bulk magnetization is 0. All right. So there is what you might think of as multipolar orders. You can also think in terms of orbital currents having this kind of ordering. So in fact, you can think of this proposal, for example, from Chandravarma for loop currents in the cuprates, where you have orbital currents running around on plaquettes in the copper oxide plane as a version of an orbital version of an altomagnet, where each loop current has some magnetic moment that points out of the plane or into the plane. And if you do a 90-degree rotation about the center, followed by time reversal, you get back the same state. So you can think of these as orbital analogs of the spin altomagnets that I was flashing earlier. And if you generalize this to 3D, you can think of like these octahedra surrounding a metal ion, and you can think of loop currents on faces of these octahedra, and they have the same symmetries as an altomagnet, except now it's in a three-dimensional system. Similar to what I showed about surface termination, if you take a 1-1-1 surface termination for these kinds of systems, you can have orbital magnetization instead of spin magnetization that I was showing earlier. You can have orbital magnetization and potentially sort of Kerr effects for certain special surface terminations in these systems. So let's then turn to sort of, are there interesting materials and are there interesting sort of questions one can ask beyond this kind of general discussion about multipolar orders. And so, of course, the playground that we are working in are these Mott insulators, where you can sort of typically focus for the purpose of this discussion on the T2G orbitals, where you end up, if you look at only the single particle physics, with a J3 half quartet and a J1 half excited doublet. But now you can kind of put in these orbitals and turn on interactions if you have multiple electrons, and one can write down sort of all the degeneracies of the ground states that you expect once you project to the T2G orbitals and include spin orbit and interactions. And so you end up with the fact that if you look at the D1 system, then this has a J3 half. Naively, the D2 system has a total angular momentum 2, 3 half for the D3, but the other ones have either total angular momentum 0 or form a Kramers doublet with angular momentum half. So if you want to think about multipolar orders, as was mentioned earlier, we would really want angular momentum greater than equal to 1. So these are all candidates potentially for realizing this multipolar order. So how do we know that this picture of multiplets, is it correct? And one way to do that is to kind of do a Rick's experiment, where you can sort of measure the entire excitation spectrum out to some energy. And this has been done on a number of these double perovskite compounds, which have kind of reasonably isolated octahedra. And so they feature fairly sharp lines, as seen in the experiment. They have fairly sharply defined kind of spectral lines, and you can compare that with a simple sort of exact diagonalization on like single site, and you can sort of match to the kind of spectra here, and you can largely sort of confirm that, okay, these are ground states and excitations are kind of in complete agreement with. So what we want to, so this is kind of single site physics, and now we can start asking about what happens when you include sort of interactions between sites. And when you do that, I'll kind of discuss briefly some work on the D1 systems, and then I'll turn to sort of the D2 materials which we have been working on. So if you look at a D1 system, then it has an angular momentum J3 half, and there was some early work from Vesna and collaborators where they had found that, in fact, the system, as you cool it down, let's say in zero field, as you cool it down, instead of just forming like a simple antiferromagnetic order of some sort, it features some kind of broken crystalline point group symmetry as seen from NMR. followed by kind of a phase transition into a magnetically ordered state, which has sort of dipole moments that point along a certain direction. And so the idea was that one could have these kind of two-step transitions in these J3 systems. This has more recently been seen also in this other compound, these barium magnesium rhenium oxide. So this is some work from Zenji Roi and collaborators, where they find clear evidence that if you look at the crystalline symmetry of the system, there is a clear higher temperature transition where crystal symmetry is lowered, not unlike sort of this higher transition seen in these in the sodium osmate, followed by a lower temperature transition, which in this case is sort of well separated by about 15 Kelvin into a state which again exhibits sort of dipolar order. And so the order that's inferred is that you have some combination of the x square minus y square and z square orbital degrees of freedom, and that quadrupole order is at a higher temperature, followed by a lower transition into dipolar order. But more recently, there's been a lot of work sort of trying to understand how phonons kind of enter this picture, and they enter in an important way in terms of determining the nature of this broken symmetry phase. What is the precise form of orbital order in the system? In fact, does depend on sort of incorporating the effect of phonons and looking at sort of this competition between Jahn-Teller and the interaction effects between neighboring sites. So the work that we've been focusing on are the D2 double perovskites. So naively, if you have, so this is the double perovskite structure where you are kind of occupying, your magnetic atom sits on one sublattice of a cubic crystal. And so that forms an FCC lattice. And if you put 2 electrons in the J3 the simple types of counting, either if you do like total L, total S, and you add them up, or you think of 2 electrons sitting in the J3 and you want to add it up that way. In either case, the result is that you get some total angular momentum 2 for the ground state. And so you expect a 5-fold degenerate level. But when one looks at sort of the specific heat of the system, you see that there is some transition that happens at about 30, 40 Kelvin in some of these osmates. But if you integrate up to get the entropy that is recovered when you heat to, let's say, about twice the transition temperature, the entropy is nowhere near log 5 that you expect for this angular momentum. In fact, the entropy is somewhat closer to log 2 rather than log 5. This tells us that this simple picture that one has for this degeneracy of the ground state is somehow incorrect. Second puzzle is that there was work from USR where people found that when you go below this phase transition here, there are oscillations that show up in the MUSR signaling time reversal symmetry is broken. But the induced, the internal fields that one infers from these oscillations are actually extremely small. So they are not as large as you expect from like a Bohr magneton worth of magnetic moment. So this was kind of an interesting puzzle, and Bruce will touch upon it some of this in more detail in his talk later in the week. But one way we thought would be a kind of nice way to resolve these puzzles is to kind of realize that this J equal to 2 angular momentum state is a little bit like a d orbital in a cubic crystal field, and in fact it should split into an EG-like and a T2G-like levels. But of course, this is not the original d orbital. So there's nothing that tells you that the triplet has to be lower and the doublet has to be higher. There is no particular rule. In fact, this we can understand from microscopics in more detail that in fact, the correct order of splitting that happens to this J equal to 2 is that this EG-like doublet is lower in energy, and there's a T2G-like triplet, a magnetic triplet that's higher in energy. And if this happens, then we can kind of understand much of the physics of these systems, because the doublet that forms here is a non-Kramers doublet. So it's a state where one member of this doublet, one of these wave functions has Jz equal to 0, and the other wave function here is a linear combination of plus minus 2, Jz being plus minus 2. And you see from here that this cannot carry a dipole moment. This particular state will have no matrix elements for dipole moment. And so therefore the ordering you expect from time reversal symmetry breaking is somewhat more complicated. It's some linear superposition of these, but it's not associated with dipole order. And moreover, you can kind of understand that if this splitting happens, which is perfectly allowed in a cubic system, then the entropy that you will see, unless you heat to very high temperatures above this gap, the entropy that you recover will in fact just be log 2. And so we can kind of understand that if this is the structure of this multiplet, then in fact we can kind of begin to rationalize some of these otherwise puzzling observations from the experiments. So we can look a little more detail at sort of what are the, what is the symmetry of the operators that act within the space of this doublet. And so there are 3 Pauli matrices, and 2 of them transform like a quadrupolar charge density. So they transform as the x square minus y square and the 3z square minus r square densities. But the third one is an Ising magnetic octopole. So it only has a sign. It's either plus or minus 1. And it corresponds to taking these 2 states and adding them with a relative phase of plus or minus pi by 2. And this state here preserves perfect cubic symmetry. So the cubic symmetry is not lost as you cool through the system if you develop this particular order. And in fact, the pattern of magnetic moments or the magnetic field that you expect from this order is precisely this pattern that I was showing you earlier with sort of orbital currents running around on the octahedra. It's precisely one where you expect that along these 1, 1, 1 directions, you would expect magnetic moments that are pointing into or out of the octahedra. And so that's kind of our proposal was that there is this kind of ferro-octopolar order of these non-Kramers doublets is what is important in these systems. So there was some phenomenology that we had kind of worked out, which kind of was in reasonable agreement with experiments. But one can sort of do a little better. One can sort of go on and kind of do microscopics. And in fact, the first work on this was from Leonid and Dario and Cesare on this, where they used LDA plus DMFT to in fact sort of find that in fact this ferro-octopolar order is indeed stabilized in these systems. And we had kind of parallel work showing where you can have some tight binding models that you can write down, where if you include interaction effects and just diagonalize like a 2-site problem carefully, we also found that there are regimes where as you tune these different hopping parameters, inter and intra-orbital hoppings, there are regimes with anti-ferro quadrupolar orders, but there are also regimes with ferro-octopolar exchange that emerge where this order is stabilized. We did some Monte Carlo and we found reasonable transition temperatures, and there was similar work around the same time by Heyanki and somewhat earlier by Guignat, also with Heyanki's group, where they had pointed out that there might be a competition between these kind of simple ferro-octopolar orders that preserve cubic symmetry with sort of possible Jahn-Teller effects, where if those Jahn-Teller effects become very strong, then the crystal could sort of distort and you might lose this octopolar physics. So what we got from this microscopics is that at least for these osmates that we were looking at, the octopolar exchange comes out to be a scale which is about 10 Kelvin exchange. But the anti-ferro quadrupolar terms turn out to be somewhat smaller in magnitude. And of course, this is sort of our estimate from these tight binding. The LDA plus DMFT gives values which are like a factor of 2 different from this, but it's kind of within the same, it gives the same phase diagram in terms of suggesting that the octopolar order is in fact the ground state of the system. So there is in fact not just the osmates, there's in fact very recent work on these so-called vacancy ordered halide double perovskites. So these are, instead of oxygen, you have chlorine, for example, in place of the oxygen. And the double perovskites, if you remember, take a cubic lattice, and you have two different transition metals that sit on the two sublattices. The vacancy ordered ones are where one of those sublattices is in fact just empty. So it's just an FCC lattice formed by these octahedra surrounding the transition metal, but the other sublattice, which was occupied in the previous instance, in this case, is just an empty site. So these are vacancy ordered systems. And there were puzzles even here that, so these are more recently synthesized and studied. So this is work from Tony Cheetham and Ram Seshadri at Santa Barbara, where they found that, if they look at the magnetic moment in these systems, you expect that if there was a J equal to 2 magnetic moment, you should have kind of seen this in susceptibility measurements. But in fact, what they find is that, and that's kind of the expectation, is this kind of line, the black dots are the data. And if they follow the data, they in fact find that the magnetic moment seems to be crashing. As you cool the system, it seems to be crashing the temperature as you lower temperature. And what we found is, in fact, even this behavior of the magnetic susceptibility, one can understand because, remember that if you have this 5-fold doublet with J equal to 2, in fact, the magnetic moment is significant. But if it splits into a lower doublet that's non-magnetic and a magnetic triplet that's, excited and off in energy by 100 or 200 Kelvin, then in fact, as you cool the system, the magnetic moment will vanish because there is no dipole moment in the ground state. And so if you do this, you can kind of show that, with some modest assumption about the scale of the gap, you can actually reproduce with this green line, you can kind of more or less reproduce the data that's been measured. So there are other systems other than the osmate double perovskites where we think this physics could be playing a role. And but in these systems, the exchange interaction is actually weaker by about an order of magnitude. And so we predict that once they cool down to sufficiently low temperatures, they should probably see this ferro-octopolar order emerge even in these systems. So with that, I want to kind of switch to three things that I wanted to mention related to our work on this, which is that since strain and phonons can couple linearly to the quadrupoles, right, we can look at various ways in which strain enters the problem here. Right? So one is you can say, well, imagine I have a bulk crystal, and this crystal has some surface at which it is terminated. Then at the surface, you have lower symmetry than in the bulk. And you could ask, well, how does that impact? How does that surface strain impact the physics? You can look at impurities where, let's say, you take some bulk things and you have doped impurities. And I'll turn to some experiments from Wessner's group on this, where you can look at sort of NMR on impurities. And you can kind of infer that inhomogeneous strain fields play a role in that problem. And finally, I'll turn to sort of phonons and how one can use this to either detect or drive multipolar orders by driving the phonon degrees of freedom. So here is the main takeaway message from this symmetry lowering at the surface. Okay, so what you expect is if you have a cubic crystal, then you have this non-Kramers doublet that's protected by the cubic symmetry in the problem. But if you reach a certain surface, so for example, if you terminate at a 001 surface, then that surface has lower symmetry than what is required to sustain this doublet. And so this doublet is going to split at the surface and close to the surface, but certainly at the surface. And so what that will do is it's going to take this octopolar order. So think of this doublet as living on a Bloch sphere, and the octopolar order is like you're pointing north or south. So those are the two octopolar ordered states. And what the strain does is it kind of tilts you away and kind of wants to point along the equatorial direction, which is the quadrupolar ordering direction. So what the spin does is that in the bulk, it might be pointing up or down globally. But when you come to the surface, there's a field that tips and puts you towards the equator. So you should think of this bulk ferro-octopolar order in the system, but with this kind of surface-pinned quadrupoles, where there's a strong field that pushes you to align away from octopolar order. So what this means is if I now take a bulk system and I kind of just keep thinning it down, you expect that, in fact, eventually this field will kind of percolate into the bulk, and you will stop having this octopolar order. And there'll be a strong thickness-dependent suppression, which you can sort of, from Monte Carlo on these films, you can kind of see that, okay, as I look at different thicknesses and you come down to a few layers, you find that there's this very strong suppression of this octopolar phase transition. And so that would be one possible way to look for this competition between quadrupoles and octopoles. Turning to this impurity systems, it's what we were kind of dubbed like a Janus impurity, which is, it has both good and bad aspects to it, right? The good aspect is that, if you have impurity ions which have NMR active nuclei, then you can use it to probe the local susceptibility or the local spin dynamics. On the other hand, the very fact that you've put an impurity lowers the crystal field symmetry. The point group symmetry is lower, so you end up sort of splitting the non-Kramers doublet. And now you can ask, can you still extract some useful information, or can one try and make sense of data that one might have on these systems? So this is kind of the data that I was referring to from Vesna's group, and Cesare was involved in sort of looking at some of this data, and they have sort of later work, which I didn't include a reference to, but they have work kind of looking at this entire doping series. There's a follow-up work from, again, from last year. But this is NMR now, where you go from, interpolate from the old work that Vesna had, looking at, no calcium. This is just barium, sodium, osmium oxide. At this end is a 5D1. At the other end is the 5D2, where you don't have sodium at all. And that we know has a transition temperature of about 40 Kelvin. But since the sodium ion is the NMR active ion, which one can probe, one can kind of think about working close to this limit, and I'll restrict myself to this regime here. If you work close to this limit and put in like a few sodiums, it's like you're putting a few impurities, and then you're asking, can I probe the physics of this bulk order that's present at x equal to 1, but I'm doping a few impurities and asking, can I probe the physics of that bulk order without disturbing it too much? And so crudely, what is seen is the following, that you can look at this NMR line as a function of temperature. So this is at 0.9, which is kind of sitting, this one here. And you find that, okay, there is a sharp line at high temperature from just motional narrowing at high temperature. As you cool down, there is a slight shift of this, the peak of this NMR line. And then as you cool to below the transition temperature here, where time reversal symmetry is broken, this line broadens enormously. So that's kind of the phenomenology that, roughly you want to ask, can I capture this phenomenology by thinking about octopolar order or this competition with quadrupolar ordering in the vicinity of these impurities. So here is what we did, and this is, I'm drawing cartoons here, but this is really things that came out from looking at DFT calculations with these impurities put in there. And so here is the, the ideal crystal, where these purples are the osmium, and this other one in this particular instance is a calcium. So this is magnetically inert. So these are the two sublattices. One is the D2, the purple one. This one is just completely inert. And what is done is to replace that magnetically inert green side with sodium, which is this yellow side. Now, of course, this induces charge doping. So that's a separate issue that I will not touch upon. But one thing that's already clear from just the structural study of this problem is that it induces distortions in the system. Right? So if I take a single impurity, I replace green by yellow. It's a different size, different charge state, and so on. It induces a distortion of the octahedra in the vicinity of this doped sodium ion. That's fine, but more importantly, it also induces distortions that break. So here it doesn't break the point group symmetry around the sodium ion, but it definitely lowers the point group symmetry around all the neighboring osmiums. So what you expect is that these neighboring osmiums, even if they had octopolar order to begin with, will have the same effect that I was mentioning earlier, namely it's going to tip away and become quadrupolar, pinned to the quadrupolar direction at these places. If you put in more and more of the sodium, eventually the crystal symmetry will be even lower locally in the vicinity of pairs of impurities. In fact, the crystal symmetry is even lower. So what does this do? So there is clearly a coupling between, for example, if I look at this distortion here, it looks like an x square minus y square distortion symmetry. There is an odd component, it's parity odd, but if you project to the d orbital, that part goes away. And so what you're left with in this particular instance is like an x square minus y square distortion, and that will couple to the quadrupole tau x. Right? Similarly, there will be a z square minus r square strain field because it's a three-dimensional system, which will couple to the z quadrupole moment in the system. So what this does is it says, well, local strain fields of these two symmetries will directly pin the quadrupole order. There's another effect if there are off-diagonal components, right? So if there is a strain of the form epsilon xy, which happens if you start putting in more of these impurities, there's also epsilon xy type strains, but those strains couple the non-Kramers doublet to the excited magnetic triplet. And what they do is they induce a small dipole moment in the non-Kramers doublet. So earlier, the non-Kramers doublet did not have any magnetic moment. But once the crystal is distorted with this distortion, it induces a small magnetic moment that depends on the symmetry of the local strain. So if the strain field is epsilon xy, you induce a magnetic moment, a dipole moment along the z direction. If it's like an epsilon yz, you will induce a jx. And so the strain field will directly induce sort of a local dipole. But since these strain fields are random, you expect that these dipole moments will point in random directions within the solid. The induced dipole moments, which are like the parasitic dipoles, will be pointing in random directions. So with this, we can kind of understand the, actually there's a cute analogy to how to think about these induced dipoles in an altamagnet. Actually, there's a much simpler, with a spin altamagnet, which is that if I put in an impurity that lowers crystal symmetry, let's say I just knock out one of these sites, you see that, oh, I'll produce a dipole moment in this problem because I've broken the C4 symmetry. Okay. So there's an analogy one can make, but here it's somewhat different, but at least there's a simpler pictorial way to think about this. So with that, we can kind of understand two things. One is there's a very sharp reduction of PC, and we can kind of understand this because every time you put in this dopant, there are 6 neighboring sites that get pinned along the quadrupole direction. And so it's like you've taken a big chunk of this octopolar system and you've knocked them out of the system. And so when you do that, you can very rapidly suppress TC. And this is just some Monte Carlo calculation of the doping-dependent reduction. And it's kind of roughly in line with the kind of reduction in TC that is seen here at this end. But one can understand more details about the spectral line. I mean, these are kind of simulation that I can kind of go over this in more detail later if people have questions, which is that at high temperature, what we do is we take these impurities, we kind of run the Monte Carlo, so we know precisely what the ordering and what's happening at each point in this whole system in the presence of impurities. And then we look at sort of the NMR on the sodium, what's the expected NMR signal, and then we'll get some histogram. And what is being plotted is kind of the theoretically calculated histogram, making some reasonable assumptions about the hyperfine interactions. Okay? And what we see is that there are 3 effects. One is that as you cool, what you expect is that in the presence of the sodium, we saw that there was some breathing-like distortion around the sodium. And what that gives rise to is it depends on what the local quadrupoles are doing. And so in effect, there is like an NMR splitting here that acquires a temperature dependence that's closely tied to the night shift that's closely tied to the quadrupolar susceptibility in the neighborhood. And that kind of explains this 1 over the night shift having a linear temperature dependence at high temperature. And that's also reproduced within our calculation, that you see that this quadrupolar susceptibility growing like, growing like 1 over T as you cool gives rise to this kind of shift in the center. It's kind of a weak shift because just the hyperfine interactions with these quadrupoles, I mean, it is a small effect. But that's one effect. The second effect is this very strong broadening when you go below TC, and that we attribute to the formation of these random dipole droplets that form, which point in very different directions at different points in the system. And so this random dipole droplets actually give rise to this very strongly inhomogeneous internal fields that you generate in direction. And so there is, of course, a magnetic field that you apply from outside, but these internal fields are pointing in random directions. And so in the end, you find a very broad distribution of internal fields that emerge in the system. So with that, let me turn to now asking, okay, so we kind of know that this quadrupolar physics plays a role. The question is, can one look at sort of the physics of this if you pump the system or you can drive the system in some way? So we've been looking at now sort of, at this point, these are toy models where we can kind of have some sense of what these coupling constants are. But here is a model where we kind of have some e.g. phonons, and we will just think of these as classical degrees of freedom for the moment. And these phonons have a displacement that couples linearly to the quadrupoles as before. And now we can ask what happens if I take one of these phonon modes, let's say the x square minus y square phonon, and I come and hit it with a pump beam, right? What will happen to the system, right? So normally if I have a cubic crystal and I hit this thing, then an x square minus y square phonon will not transfer energy to a z square phonon because these are just completely orthogonal modes in the problem. Right? But in the presence of octupolar order, you can have the following sequence of events where you pump an x phonon, the x phonon kind of tips your quadrupole in the tau x direction because of this linear coupling. But if you have octupolar order, then the pseudospin is going to precess around the tau y axis. And that gives you a way to transfer energy from the x square minus y square to the z square phonon. Okay? And so what you expect is this kind of phonon thing where the blue phonon is the phonon that I kick with my pump beam, and it periodically transfers energy back and forth between the two phonon modes, which were otherwise orthogonal. And now you can transfer energy between them. And that depends on, the strength of this transfer depends on the presence of octupolar order. So at high temperature, it is absent. At low temperature, there's this coherent back and forth transfer of energy. And one can moreover kind of use this, in a different way where you say, well, I can transfer energy between x and z, but can I use this as a way to drive the system? In other words, if I were to drive these two phonon modes with a certain phase choice, can I actually induce octupolar order? And in fact, we can kind of do this analysis, either within a Floquet-like picture of driven phonon problem. But in the end, what we find is, if you start with a certain octupolar order, you can basically, over a period of time, which is, tens of picoseconds, you can basically switch the octupolar order from being, let's say, pointing up to pointing down with a particular phase choice for this thing. So it gives a way to kind of detect and probably even control this octupolar order. So let me, end here. So I would like to thank my collaborators. So all this work that I was talking about was done with my students at Toronto, Srikar, and all the work on dynamics, which I'm going to mention at the end, was done with Kathleen and Rory Sutcliffe. We kind of got started around, thinking about these systems, these double perovskites, through a collaboration with Bruce Goller and his group. And I guess Bruce will touch upon, some of the measurements from his group here. And the work on this impurity NMR was with Tanushree Sadasgupta, and this more recent dynamics, we've been also collaborating with Gil Rafael at Caltech. With that, I'll